Hello everyone, my name is Franco and today I will present this traffic system that I made a while back when I was at school. So before looking at the setup, I wanted to quickly show this boids example. This was originally presented by Reynolds in 1996 and he wanted to simulate the flocking behavior of birds. In any case, I believe that some of the rules used by the system apply in one way or another to all living things, so we will take a look at the three simplest rules, which are separation, alignment, and cohesion. Okay, so I am going to play this for a minute and let's see what's gonna happen. Keep an eye at the top here because this will change over time. Okay, so let's go back to the beginning and see what's going on. First, it looks like the points are moving kind of randomly, right? They don't seem to have any special behavior. They are picking up the colors, but we will see that soon. So if we continue, separation comes on, and we can immediately see how the points just try to stay away from each other, right? They don't want to just come too close to each other, while they still move randomly. Continuing, the alignment rule comes on, and we can see how the points go from this just crazy movement to this. And this is because each point is kind of trying to follow the direction of the points near them, so the velocities become aligned, and this is why they all kind of flow in the same direction. And then if we continue, cohesion will be enabled, and then we can see how all the points try to form groups. We can see pockets of them forming up. Let's have a look at how to implement this in VEX. So the inputs for the simulation are quite simple. It's just some points here on the left and some geometry on the right, which is some tubes and a grid to define the edges. So if we go inside the POPNET, we can see there is not much going on, but let's start at the top. We have a pop force, and this is what is driving the movement of the particles. We saw at the beginning the noise movement, so yeah, this is what is creating that, very simple. Then the next node is this repulsion node, and this is actually our first rule, the separation one. So the way I'm doing is, I'm using a PCOpen function. And this PCOpen function will, for each point, we'll look around it in a radius, and we'll store X amount of points, right? And this radius is defined here, down here, and the number of points is defined here. So it will store up to this amount of points, which I define randomly here. And all the points that it finds, it will store them in this handle variable, okay? So then with this handle variable, we can iterate over it, because this is basically all the points that we found. So we just want to go over all of them and do stuff, right? And actually here, before going in there, what I'm doing here is checking if I actually found something, because if I didn't find anything, then yeah, I don't need to worry about trying to do stuff. So yeah, I check if I found something and I start iterating. And then once inside the loop, what I'm gonna do first is I'm gonna get the point number of the point that I'm going over, and I'm gonna store it in this variable here. And then what I'm gonna do is I'm gonna check if the point that I found is not me, because when you do a PCOpen on yourself, which is the case here, because I define the zero input as myself, so all the points, I will find myself, and I don't care about that, because remember, this is the separation rule, and I only want to find other points to stay away from them. So if I didn't find myself, what I'm gonna do is I'm gonna get the position of the point that I found, and I'm gonna store it in this variable. And for that, sorry, I should say I'm gonna use the PC import function, okay? This will import an attribute that you choose from the handle, and you're gonna store it in this variable up here. Okay, so once I have this direction, this position, it's very easy for me to make a vector that will point away from this position, because I can just subtract it from myself. And this is what we want, because yeah, we essentially want to go away from other points. So this vector will help us do that. So with that, the next thing I'm doing here is a distance variable. And this is basically a ramp, because what I can do here, if I ramp the distance from me to the point that I found, I can then decide, oh, if I'm too close to the point, I want the effect to be higher. I want to get away from there quick. But if I'm a bit far away, maybe I don't care as much, and then the effect will be lower. And this will help having a more smooth movement when points are trying to get away from each other, right? So then finally, what we have to do is add to the force this direction, basically the vector pointing away from the point that I found, and then I multiply it by the distance, which is the ramp that we made previously, and then another multiplier, which is this channel here, which in this case is just is keyframe to come in effect at frame 1080. So we can see as soon as we reach frame 1080, this will go up to 4, and that's why we're getting this separation in the points. Okay. The next rule is alignment, and this one in a way it's simpler. We're still using PC open, and we're opening a handle around ourselves in a given radius and finding up to this many points. But what we want to do here, remember, because this rule, what we're trying to do is to make the points go in the same direction. So what we can do is first check if we found something. And if we did, we're gonna use the PC filter function. And this function will return the average. So we're gonna give it the handle, so basically all the points that we found, and an attribute. So this will return the average velocity for all the points found around ourselves. And we're storing it in this variable here, average v. So then we can subtract our own velocity, and we will get a direction vector. And this direction vector will essentially point us to this average velocity. So this way, when we add it to the force, we will eventually align all the points in the same direction. And the cohesion rule is very, very similar to the alignment one, because if you remember, what we're trying to do here is we want the points to form groups. So to do that, well, first we open a handle, just like before, right? And if we found something, then we're going to use PC filter on the handle, so all the points that we found, but this time with the position attribute. So this will essentially give us an average position of all the points found around myself. So then with this vector, I can subtract my position from it, and this is going to give me a direction vector that points in this average position. So then I can use this vector to add it to the force, and this will push me towards this center, so all the points will eventually make groups. And something else that I'm doing here that I did before for the separation is that I'm doing a distance ramp, so points that are close to the average position won't push as much because they are already close, and points that are far away will have more force basically, so they will get there quickly. Now I just want to show a couple more things here, and then we'll just go to the traffic system. Okay. This is stay away from bounds. What I'm doing here, I'm opening a handle, but this time I'm doing it in the first input, and this is defined here as the second context geometry, which is basically this line and these tubes. So from there, I'm only finding one point. I only want to find just one point, the closest one to me. And then if I found something, I'm gonna grab the position of that point just with PC filter. And then I'm gonna do the same that I did for the separation rule. I'm gonna create a direction vector pointing away from this position. So then this way I can always be sure that I will always stay away from the edges and I won't go inside the tubes. I'm also doing a distance ramp, but yeah, I think you get the idea. And the next thing I want to show is the colors. This is just doing the same. I mean, it seems a bit overkill to use PC Open for this, because it's basically opening a handle on the first input, which is the geometry, the tubes and the white edge. And then it's going in, it's grabbing this color with PC filter, because it's just looking for 1 point, so the closest one, and then it will apply the color, right? That works, but it's a bit unnecessary, because then we can do the same thing with a simple near point function and we'll get the same result. If I just connect this here instead, same thing. So yeah, sometimes you have to see what options you have, because PC Open can get heavy if you have many points. But what PC Open it will be nice for is that since we have this PC filter that will average the values, we can use it, because you can see all the transitions here for the colors are kind of hard. It's just one color or the other. But if we enable this, if this time we just get all the points around me, basically, well, not all of them, up to this much, but in this radius, so it will be something like this. So we're gonna get all these colors, and then we're gonna use filter to average them. So this way, if I toggle this, I don't know if you can see, but there is a change in there. Now the colors are not so just one or the other, it's just more like a gradient. You can see especially down here. And yeah, that's pretty cool. So I'm gonna go up here and then show you just how this will look if you do just a trail, because it's a cool motion. And you can also see here the gradients in the colors, because I use the PC filter. I'm sure there are other ways to do that, but yeah, just this way it's simple enough. Okay, so we're gonna stop this here, and then next we're gonna take a look at the traffic system. Okay, so the traffic simulation. I know this is not like the one we saw at the beginning of the video, but it's essentially the same system, but I just made a simpler scene so we can have a look. I also don't think I'm gonna have time to go into detail into everything, but it's gonna be more like an overview of what's happening here. So geometry-wise, it's not much going on procedurally. It's just a grid, right? So this is some grids and some lines. But these lines that you see here, the colored lines, are important because these are the lines that guide the vehicles to drive on the streets. So the lines, they have groups, and they also have attributes like street name. And these are important because they're used in the simulation to tell the cars what street they are driving on, and also where they can go next. So then we also have the traffic lights. These are, I made kind of like a little subnet here so I can easily copy and paste new ones. And yeah, they just have a street name so they know what street they belong to, and this can be also used in the simulation. And right now I just keyframe the state of the light. It could be done procedurally, but yeah, at some point I just didn't have more time to work on this. Stop signs, essentially the same. They know what the street they are on, so can be used in the simulation. And I'm actually gonna add a new one here so we see earlier what's going on. For pedestrians, well, actually let's play the simulation a bit and see what's going on. Yeah, this is very slow. Let me increase the speed. here all that's happening is that this is reading the result of the simulation, and there is just a read time, so nothing special. So yeah, as I was saying, the pedestrians, I'm not gonna go too much into them. Here is one, because they're essentially the same. All I did for them was I grabbed the car simulation, I pasted it and tweaked it a bit. It's just the same. Instead of having a car model, they have a person model. And that's why Houdini is so cool, because you made a system and then you can just reuse it for many different things. But well, as we can see, the cars come in the simulation from the end of the road, and then if they are green, it's because they are accelerating or just moving. If they are yellow, it's because they are slowing down, and if they are red, it's because they are stopped. There are some blue ones too. That means that they are at their maximum speed that they can travel. And we can see how they come here and they stop for people in the crosswalk. And wow, something popped in there. Was it me or? Okay. Well, you can see how they just stop at different distances, and then they will start moving again once this is clear, which, yeah, I guess they are seeing this guy. But yeah, we can see how they also come here to the stop sign. They stop there for a little bit and then they continue. And then at the intersection, right now there is no left turns, still something I have to implement, it's just right turns. But yeah, we can see there's a red light, these guys will stop, there's a green light here, so these guys will go or they will decide to turn. And this is why the attributes on the lines are important, because this way they can decide if they want to go straight, or they can see, oh, there is a street here, I can go this way, so they will randomly choose if they come here or if they go straight. So yeah, let's have a look at the simulation setup. So here we have the inputs, and the first thing we have is the points where the cars are gonna enter the simulation. So you can see it's small, but you can see 2 here, and yeah, 2 more here, 2 more here, and 2 more here. And these points, they have street names. I hard-coded this. I wanted to do it procedurally, but that's something to do in the future, because yeah, it could easily be done from this line. But yeah, I just hard-coded it. To each point, I told it which street they belong to, and I gave them a group. So we can also use that in the simulation. And then the next 3 inputs are the guides, the colored lines for the cars, the traffic lights, and the stop signs. So if we go inside the POPNET, this is where everything happens. You can see all these pop wrangles, and this is basically little snippets that will do one small and simple task. So this way I can easily expand it and add new functionalities, and it's easy to work with. So as you know, this will be executed from top to bottom and left to right. I'm gonna show you first these 2 branches, and then this last one here, and then these 3, and I will explain why as we go on. So if we start here, this is where all our pop sources come in, right? I defined some expressions here, so I can choose how often cars will come in, how many of them, and this is linked to the points that I place up here, because these have a group like this, and then each one of these guys here also reference the groups, so they're connected. Okay, so after that I'm assigning a car ID attribute to each car. Basically, I could have used ID everywhere, but I thought I will make my own. And next, with that car ID, I'm assigning to each point what kind of car they are. So I give them a name and a p-scale. This is the real size for the cars that I Googled. So apparently the mean is 3.83 meters. And this works because all my car models are normalized to 1 meter long. So this will scale them up to the real size. And next, I'm assigning here some speed max attribute. And this is an attribute that the pop solver understands. So this will basically work as a speed limit because the solver won't let any point go faster than this value that we defined with this attribute. So in this case, I'm giving each car a random value between 11.1 and 17.7 meters per second because the solver works well, the velocities work in meters per second here. So that turns out to be 40 kilometers or 25 miles to 64 kilometers or 40 miles. And then next, I'm assigning some attributes here from view angle and from view distance. And this will be used later on when cars are checking for things around them. And the next one, similarly, it's more attributes to define different things, like how close a car needs to be from me before I start braking, or how close I can stop to other car, behind other car, or how fast I'm gonna start moving after the car in front of me is moving so I can go. And then same thing for the lights, how close I'm gonna like stop in the light. Am I gonna stop here? Am I gonna stop here? Am I gonna go over it a little bit? All these things are defined here randomly per car. So here are the values. The next branch here, starting with the go to road node. The first thing, which is actually quite important, is the group box. This is limiting all of this code to cars which are in the state moving or braking, right? And we will see this soon when we see over here in this branch. Okay, but for now, what this is doing is it's basically saying, find me the closest point in the road that I'm supposed to be. And then with that point, give me a direction vector to that point from my position. So then we can use this, just like we used it before in the boids example. We can use this vector, which is pointing to where I have to go. We can add it to the force, and this will already push me in that direction. And then I'm adding a multiplier because I want it to be fast. And then another force multiplier, which is essentially fitting it in the distance. So if I'm already kind of close to the road, I don't need to push as much. Okay. And then once we are in the road, what we're gonna do is we're gonna use the average direction, which is also calculated around here. But we're gonna use this average direction, which is grabbed from the road and calculated here, like I said. And we're gonna just add it to the force as well. So this way, we're not only going to the road, but once we are in the road, we will follow it. And then multiplier, so we can choose how strong the following force is. And lastly here we have some normals set up, so we can either decide if we are moving, we're gonna say that the normal is where we're heading, so basically the velocity. And if we are not moving, then it's just gonna be the direction of the road, just as a safe measure so cars don't turn in weird orientations. Let's go to the last branch now, this one, because everything that happens here is important for this to work. So let's have a look at this first. The top node here is basically getting the attributes from my street. I already know my street because that's defined in the source points right here. So with that, I can get my connected streets, street lane, and also the average direction, which was used before here, as I was saying. And then with this connected streets array, I can define which ones I can actually go, because just because one street has 3 or 4 connected streets, it doesn't mean I can go, because maybe that one is behind me. So this code here is checking for that, just making another array of the actual available streets to go. Okay, and then with this new array of available streets to go, I will randomly choose one from there. So we're gonna make a random number here, and we're gonna choose a random entry in this array, and we're gonna store it in the next street follow attribute. Okay, and then with this next street follow attribute, we're gonna go to the next node, and here we're actually gonna be checking all the time, hey, am I close enough to the next street? Am I close enough? Am I close enough? And when I'm close enough, this will come in here and it will say, okay, I'm close enough. So the street follow now becomes the previous one, because I'm gonna change to the next street follow. So then I assign the next street follow to the street follow, and then you can see how this will loop back here, and now the car is gonna follow this, which I just changed it here. Sorry. So this will always continuously loop, and check for things, and it will update all the time as it comes to new streets. The next node is checking for the closest lights. So first I'm saying, hey, what's the point number of the closest light that matches the street that I'm following? Okay, so that gives me the point number, and with the point number I can get the position. So now I have the position of the closest light in my street. So with that position I can calculate the distance. And what's interesting here is that I not only do the distance, but I also make sure to subtract half of my p-scale. This way the distance will be accurate from the front bumper of the car. And then I'm getting the state of the light, so I know if the light is red or green. And then I'm calculating a dot product between my direction and the direction from myself to the light. So then I can say if this dot product is positive, then it means that the light is in front of me. If it's not, then it must mean that it's behind. And I store these attributes, so then I can use these values later on to do different things. Next, we're gonna check for stop signs. And here is the first time that I'm using PC Open. I was actually using it before here, but I moved away from it, tried to use other functions because it was becoming a bit heavy. But in this case, it's only just 1 point, it's just fine. So I open a handle in the third input, which is the stop signs. And then if I found something, I'm gonna go in there and I'm gonna get the position of the sign, the normal, so I know which way it's facing, the distance, and this is neat because I don't need to calculate it myself. You can use this and it will give you the distance, although I ended up modifying it so I can account for the size of my car and have the correct distance from the front of the car. And then I'm getting the street to which the stop sign belongs. After that, I'm gonna do some dot product calculation because I wanna check if this stop sign is actually in my field of view, because if it's not, then I probably don't really care about it. And if this is true, then I'm gonna check if the stop sign is actually in my street. And if it is, I'm gonna do another dot product to check if it's actually in front of me when I'm next to it. Yeah, looking at this now, I kind of realize this is a bit redundant, because yeah, if it's in my street, I shouldn't have to check, but yeah, I must have done this for some safety checks, I'm not sure. The point is that I'm determining here that the stop sign is actually in front of me, and then I need to stop for it when I get there. And now finally, we're going to check for other cars in the simulation. So we're gonna do another PC Open, this time from ourselves, we're gonna find up to these many points and to this distance. So this was defined back here, if you remember. So yeah, with the handle open, like always, we're gonna check if we actually found something. And if we did, then we're gonna iterate. And the first thing we're gonna do is just check for the point number, because again, if we found ourselves, I don't care. I don't want to do anything. So if what we found is not ourselves, it means it must be another car. So what I'm gonna do next is I'm gonna say, hey, what street are you following? Give me your street, and I'm gonna store it here. And also the lane. So with that, I can check, is my street the same street as the car that I found and the same lane? So if it is, then I need to do more checks, because this car may actually be just in front of me or very close to me. If it's in another street, then I don't care, because there's no way it's gonna be in front of me. But if it's the same street, then I need to continue doing checks to decide whether or not, well, basically to store different information, so then I can decide what to do with that. So with a position, I can calculate a direction vector and a dot product. And then from that dot product, I can do an angle. And then if this angle is small enough, then it means that the car is actually in front of me. If it's in front of me, then I'm gonna store all this information, like the street that is following, the lane, the state, so I wanna know what the car is doing, the size, the distance, the point number, and the position. And then I'm gonna calculate the actual distance to this car. So same thing, we're just gonna subtract the vectors and subtract the p-scales for each car this time. So we have the proper distance from front bumper to rear bumper. And then I'm checking for pedestrians. And this is very similar to the rest. We're just opening a handle, but this time we are using the pedestrian simulation here. So I can actually show this. It's gonna look very similar to what we've seen so far. It's only simpler because I don't need the pedestrians to check for anything, at least now. They could, but all I want them is just to cross a street. So they're doing that, and then we can get the points here and do different checks to see if they're actually in front of me, and if they are, then I'm gonna say, hey, how close are you to me? And then I'm gonna store just different attributes that I can use later on to set different states. And after that, I'm checking, I'm actually setting a speed attribute that I can also use to define different things. The speed is basically the length of the velocity, and I'm also setting other helper attributes like the speed in kilometers, or I'm just setting if I'm at maximum speed or not, because then I can do things based on that. And finally, this states node. This is kind of the brain of the system. This is using all the attributes that I set here to set more attributes, and at the same time defining the state of the cars, which are either moving, braking, or stopped. So it's gonna use things like the distances to pedestrians, distances to cars, lights states, distance to stop signs. And using all that and doing different checks, it will decide if I'm braking for a pedestrian, or braking for a car, or braking for a light. And this becomes tricky because it's important to notice the order of importance. Like you might be braking for a car, right? But if all of a sudden there is a pedestrian before the car, then yeah, you need to brake for the pedestrian and stop for the pedestrian. So all the things like come into place here. Doing a long list, I'm defining if I'm moving or braking or stopping, and also if why I'm doing that. So like I say, pedestrian or car or light. And then with these states that get set all over here, depending on different attributes, we come to these three nodes: moving, braking, or stopped. So in the moving state, the first thing I do, I reset a bunch of attributes because I want to make sure I start over so things can just happen again. And then it will just set the velocity again, either the velocity that it had before or just start over. And then the breaking node, this is, I have different ifs here, statements for different situations. I could be braking at a car or at a light. Right now it's essentially the same, but they could be different. What's happening is that it's just grabbing the distance and it's using it to reduce the velocity and the force. This I didn't like this, but it worked in the end. I don't like modifying the velocity itself. It should be just the force, but well, in the end it worked because I'm saying if I'm with this fit, I'm saying if I'm very close to a car, then I want to brake very hard. I don't want to crash to it. But if I'm far, then I can just start slowly. And then this is how cars will stop. Because yeah, once they are braking and the speed is 0, it will enter the stop state. So then it comes here and yeah, I just hard code it to 0, make sure it doesn't move. And yeah, I think that's essentially everything I wanted to show. Yeah, it's not as detailed as I would have liked, of course. I will need hours probably to do a proper tutorial on this, but hopefully you got a good idea on how I approach this. There are many things that I see now after months of making this that I will do differently, more efficient, more elegant, things like that. But well, yeah, I hope you enjoyed this and feel free to ask me any questions.